Hello everyone. I'm going to talk today about our JChem chemical search engines. I'll go over the original JChem engines and then introduce our updated engines. JChem Base provides the starting point for anyone looking to integrate chemical handling and database searching in their workflow. Its rich Java API integrates ChemAxon tools such as calculators, extensive structure representation, and querying across a myriad of database formats. Our first generation Oracle cartridge brought these capabilities to enterprise solutions, improving performance and providing an interface using Oracle's native SQL language. The third component of our original engines was JChem Web Services, which enabled our users to incorporate ChemAxon technology easily in their web-based applications, exposing a REST API to enable its straightforward use as a backend. Our second generation JChem engine powers chemical search with modern features. All of our second generation tools run on a new engine, taking advantage of the database's inbuilt indexing tools to greatly speed up combined queries. They also provide hit-as-you-draw near real-time search results, as well as hits sorted in relevance order. Our PostgreSQL cartridge brings fast chemical searching to this popular RDBMS, while our second generation Oracle cartridge, dubbed Coral for Chemical Oracle Language, helps bring your searches to the cloud with full AWS RDS compatibility. This cloud readiness is mirrored in our JChem Microservices, which enable the power of the JChem engine in a modular, distributed fashion, enabling our users to set up their web applications in highly available fashion. You might wonder what prompted us to develop a second-generation search engine. There are several reasons why we decided to update our cartridges in a major way. For one thing, we have noted a trend toward larger databases. For instance, some compound databases that can be ordered and delivered quickly are in the low billions, and it's desirable to be able to search this space with ease. Another reason was that we found new ways to implement some functions to deliver the search results faster and with the most relevant compounds at the top of the hit list. A third reason was the need to support hosted and cloud solutions, so we felt it was important to make cloud-friendly JChem engines. You'll see how we manage that later on in the talk by developing scalable microservices and managed or high availability cartridges. And the final reason had to do with the legacy of JChem Base and Oracle Cartridge, which had many unused features. We wanted something more efficient, with only the features people need and want to use. Now I'll go into more details on our second generation cartridges. They are Coral, which is our Oracle cartridge, and JChem Postgres cartridge. We call it JPC for short. Microservices are a little different, so I'll talk about them later. Although Oracle and PostgreSQL databases have differences, we have implemented the same chemistry engine in both. So while the query syntax may look different between the two, you can be sure that you will get the same chemistry results, whichever one you choose to integrate into your system. If you do choose one of these cartridges, you will find a number of advantages to it. You will be able to handle databases of hundreds of millions of structures. Previously, JOC required to load the molecules into memory, but for the new cartridges, there's an option for low memory setup, meaning that you don't have to load all of the structures into memory through a search. Queries on these large databases will perform well, especially if it's a selective query that doesn't return a lot of hits. A lot meaning greater than 10,000. And relevance sorting of the hit list brings the results most similar to the top for easier interactive use. Coral and JPC, our second generation search engines, have some new features that you will like. They both have the hit-as-you-draw feature, which can be really useful to help you explore chemistry space. We've made some improvements in our approach to tautomers during substructure search so that some incorrect matches are prevented. We are excited to announce that Coral can work with Amazon's Oracle RDS to save you time managing your Oracle instances while allowing the full capabilities of ChemAxon's JChem technology. And our PostgreSQL cartridge has the option of running in high availability mode. There are some differences from the first to the second generation search engines. We have totally redesigned it from the ground up, and one thing that we changed is the syntax. The new syntax was needed to enable new features and ways of doing things. For example, instead of using JC compare for searches and TS to indicate substructure, we now have a statement like sample search. This means we are searching the database using the rules defined in a molecule type file called sample.type, and the substructure keyword is easy to understand. The user can configure the molecule type files to suit their preferences. They can even have more than one molecule type file on a database. The tautomer search strategy has changed in a way that we think will improve your search results, and EZ bond matching rules have improved. Here's a generic example of how the old engines and the new engines differ. In the old search, we tautomerized the query and searched each of the tautomers against the full database. In the new search, we've created a generic tautomer representation in the database. We don't modify the query before sending it to the tautomer database. You may wonder why the new way is better, but I think we can all agree that when you do a substructure search, you most likely want to get substructure matches for the search as drawn. With the old engine, it usually worked just fine, but occasionally you might have had some hits that didn't map well to the query. Here's an example of what I mean. If you do a search using an aldehyde as the query, as you see on the left side, you should expect to get aldehydes with the cyclohexyl ring on your hit list. However, JOC also converted the aldehyde to its enol form, as shown below, and searched on it. And for the enol form, the rules for substructure matching would allow substitution on the oxygen, since it has an implicit hydrogen. The target on the right is obviously not an aldehyde and cannot tautomerize to one. The current behavior with the new second-generation cartridges gets this right and doesn't match on this molecule. This new strategy with a generic tautomer does not fully eliminate extra matches due to uncommon or unrealistic tautomers, but it does reduce some overly generous matches. You always have the option to turn off tautomer searching as well if this is what you prefer. This is a relatively minor improvement, but there are improvements in the default EZ bond matching in the new engines. Previously, if you searched with an E configuration drawn for a double bond, you might have gotten Z configuration in your hit list. This is because the engine would assume that only an E or Z bond that was explicitly marked had known stereochemistry. The new default is to assume the stereochemistry as drawn. If you like the old assumption better, you just need to set the parameter DBS marked only, and the behavior will revert to the old method. Now, about the speed of the new engines. Obviously, search speed is a big deal, so this was one of the key drivers for change. About a year ago, Akos Tarche presented a comparison of the search speed of the old and new cartridges under different conditions. I will just point out some of the main points from his study. If you want to know about the full study, please check our YouTube channel. Akos selected 49 rings and substructures, which are commonly found in drugs, according to a 2014 analysis. 11 query features were also used to test the engines. All of these queries were performed against MQL's database of 42 million structures, and the queries were performed with and without hit limits to test the effect. This chart shows the ratio of the speed of Coral and JPC relative to JChem Oracle cartridge. So if you look at the left side, it shows the speed up. So a value of 1 means the same speed as the original JChem Oracle cartridge, and a value of, say, 20 means 20 times faster. The first column, labeled substructure, is about the same as JOC in timing, but keep in mind this is dominated by common substructures in that list of 60 queries, which return many, many hits. Limiting the hit list size increases the search speed by 15-fold, and the most relevant hits are returned. Similarity searching is quite a bit faster. The first columns are for similarity of greater than 0.5 with the ChemAxon CFP fingerprint. This is about 20 to 25-fold speed up compared to the original Oracle cartridge. Limiting the hit list size for the similarity search speeds up the search even more, up to 35-fold with relevance sorting. This is another way of measuring differences in the search speed. This time, elapsed time in milliseconds is shown on the y-axis. So the higher the dot, the slower the search. And the lower the dot, the faster the search. Coral is in orange, Postgres is in green, and the original JChem Oracle cartridge is in black. So you can see that the new generation cartridges are consistently faster, which means lower down, than the old cartridge when the hit count is less than 10,000. That's represented by that blue vertical line. Usually this is more than sufficient since it's hard to analyze large hit lists interactively. The hits come back ordered by relevance instead of random database order, so the interactive user doesn't need to wait a long time for results and doesn't need to sift through a lot of hits to get the most relevant ones. The previous results were for a pure substructure search. For complex queries, sometimes the structure search is the limiting factor, and other times it's not the most selective or limiting part of the query, so your speed up will vary. The point is that our structure search method still has a good speed up when combined as part of a more complex search. You can see in this testing that 3 to 10-fold performance improvement was seen on complex queries. Now I'm going to break to a demonstration of the search so that you can get a better idea of what we mean by hit as you draw. This is our JChem PostgreSQL cartridge demo site, which you can try out. And in it, we've loaded several databases and several different search methods, as well as the hit as you draw functionality and hit limits. So feel free to visit this website and try it out. So here I'm searching e-molecules with a substructure search, and I've sketched something in. And I have quick hits over here that have that substructure. Now, if I modify the substructure, the hit list will refresh. It will change as my sketching interactively changes. And if I go from e-molecules to Chembol, now I'm searching a different table, a structural table, and it quickly gave me the top hits with that substructure interactively again. So I change it a little bit, and it quickly updates the quick hits. And that's for substructure. If you switch to similarity, you have to check the similarity threshold which is down a little bit on the list. So make sure this is set low enough or you won't get any hits. I've set it to 50 or 0.5 over. And then you can see the most similar hits are showing up here. And as I modify the structure, the most similar hits are updating. And then back to the other table. Again, updates quickly and showing these similarity hits. Up until now, I've been focusing on the database cartridges. We also have JChem Microservices, which is our REST API implementation of the new search engine. We think this will be great for users who want to access our chemical technology on the cloud. And I should mention that the services go beyond structure searching and include lots of ChemAxon technology. We developed JChem Microservices to be cloud ready, so we have 3 cloud modules: the gateway, the discovery module, and the config server. Discovery and configuration services handle scaling up the machines and services as needed, so that the client application only has to interact with the gateway, and the rest is handled by the cloud modules. This is ideal for setups where you want to scale instances independently, not in a monolithic fashion. This is our current set of chemistry microservices. You can access our calculators through the microservices. For instance, log P, pKa, solubility, mass, atom counts, acceptors, donors, and many more. You can do structure searching using our DB module. This one is the REST API equivalent to our chemistry cartridges. The IO module handles incoming and outgoing structure formats to provide the most useful formats for your needs. We have 2 options for enumerating combinatorial libraries. One is based on a Marcuse structure, which is a core plus different R groups. And the second way is based on reactions and sets of reactants. Structure Checker is a module that checks for a variety of possible problems with structures and fixes or flags them. And the Structure Manipulation module is for transforming your molecules according to your custom rules. This constitutes a REST API for the new engines for non-Java users. Once deployed, the microservices architecture looks something like this diagram. You can start and scale up each individual service based on the load. Some of the services are stateless in green, and others can be run in stateful mode, such as the DB service with a persistent database. You can have multiple database modules connecting to the same database. The gateway can also be scaled as needed as a load balancer for the services. Here we see an overview comparison of the capabilities of the 3 products. It's available from our website product page and is regularly updated to reflect the latest status of the tools. This is a lot of information to view on one slide, so let's instead take a look at use case-based preferences for certain tools. So here are some guidelines for choosing between cartridges and microservices. For example, JChem Base, our legacy tool, is still the most appropriate product to use when building a Java application, since it has a Java API. Cartridges are the ideal tool when you need to add chemical search functionality to a relational database. Whenever combined searching is being performed using other fields from the database such as price, available quantities, or physicochemical properties, cartridges are the tool of choice. Microservices are the best choice when building web applications, in particular when rapid scalability to spikes or lulls in demand are required. Microservices are also a good choice when structure-only searching is being performed, especially for very large databases. Our cartridges are internally tested on databases numbering in the low hundreds of millions. While we expect their performance to remain consistent for even larger databases, the microservices perform in excellent fashion in such conditions and are routinely tested on collections of compounds numbering over 700 million. If you're a current user of JChem Oracle Cartridge, I'm sure you're thinking about the process of migration to the new tools. I know it can be intimidating at first to consider changing the cartridge, so we do have a couple of videos which will help to explain the process in more detail. The first one is a recent example by Marcus Weiser of Quattro Research, where he migrated a large pharma database. The second one is a talk by Tamas Varga of ChemAxon, going over the necessary steps for either Coral or Postgres migration. Both of these are on our YouTube channel, and just ask us for the links. Coming up in today's session, you will hear about some of our front-end applications that use JChem engines for chemical intelligence. Some of these can use the second-generation engines as well as the standard JChem base. An overview of the compatibility matrix is shown here. I'll do a very brief intro into 4 of our products that you might find useful: compound registration, JChem for Office, Instant JChem, and the KNIME nodes. The first product is compound registration. This is a fully fledged enterprise-level registration solution. It uses JChem base on the back end to handle structures, run standardizations and comparisons to existing registry compounds, and it stores chemical structures in a JChem database. Compound registration sends its data to a downstream database. This downstream database could include one of our second-generation cartridges for great query performance when combined with other non-chemical data on the compounds. Second, we have JChem for Office, ChemAxon's extension for the Microsoft Office suite. This provides chemical capabilities like sketching, calculation, name conversion, and more to the full suite of Microsoft Office software. It is compatible with JChem base and the new cartridges. From Excel, you can connect to your corporate database and search directly using JChem tools, filter by substructure, or do SAR analysis in your spreadsheets, all within the familiar Excel environment. Instant JChem is our desktop database management tool that allows you to connect to databases, perform searching, analysis, load new data, and build your own forms without programming. It takes away the need to build out a front end on top of your JChem engine of choice by providing a one-stop interface for all your needs. Instant JChem is compatible with JChem base and our second-generation cartridges. And finally, I wanted to mention KNIME, a popular third-party workflow tool. Most of our ChemAxon products are available as nodes within the KNIME workflow software. If you wish to search your database, convert and manipulate chemical structures, calculate properties, or fingerprint descriptors, you can do all of this and more with ChemAxon's chemically intelligent nodes. We have KNIME nodes for accessing JChem base and cartridge databases. KNIME also has a REST API node that you can use to call JChem microservices. If you enjoyed this introduction to the second-generation engines and you're ready to take the next step, I recommend trying out our demo webpage where you can see the Postgres cartridge in action. And of course, feel free to talk with us more about migration if you're a user of JChem Oracle Cartridge or the classic web services. Thank you for your attention, and I appreciate any follow-up questions you might have.